In this video, we're going to work about 40 convergence testing problems. So we're going to be given a series, and we need to perform a test to see whether that series is convergent or divergent. Now, each problem, there's going to be no context as far as, it's going to be completely random. We have no idea which of the tests that we have learned should be used. And so the previous video was about the general strategy that we're going to use to approach when we're given a random series on how to test it. Okay, and so just like the integral marathon and the derivative marathon videos, the level of difficulty, the type of problem, it's all completely random. So we might be given the hardest convergence testing problem first. We don't know. All right, let's get started. Okay, so looking at this, I see something over n squared, and my mind thinks about a p series. 1 over n squared is a p series. And so I'm immediately thinking about 1 over n squared. How is that related to e to the n over n squared? Going from 1 to infinity. Well, e to the 1 is greater than 1. This is always greater than 1 for all n. So this is greater than this. All right. Now, this series is convergent. However, that doesn't help us here because these terms are greater than these terms. If these were less, then that would tell us that this is convergent. So the comparison test didn't work, or that specific comparison test didn't work. Okay, just curious, let's do a test for divergence. So if we replace n with x, we get e to the x over x squared, and there's no issues there. So, okay, if we take the limit as n goes to infinity of e to the x over x squared, then we get infinity over infinity, so L'Hopital's rule. You get e to the x over 2x. Plug in infinity, you have infinity over infinity again, so L'Hopital's rule again. Okay, this goes to infinity, which is not equal to 0, so this is divergent, based on the test for divergence. All right, here I see this 1 over n, and I think, okay, we know this is a p series that's divergent. How is that related to 1 over, to this? Well, the square root of natural log of n, going from 2 to infinity, that's always positive. And it just gets bigger and bigger and bigger. So this is going to be, these terms are always going to be smaller. All right. Now we know that this is a p series that's divergent because p is not greater than 1, but this is always greater than this. So that's inconclusive. That comparison test is inconclusive. Okay, what about an integral test? And the reason why I'm thinking integral test, well, let's first see if f of x, if we can replace n with x, then is there an issue with that? No, there's no issue there. And the reason why I'm thinking integral test is because the derivative of natural log of x is 1 over x. So the integral should be easy. Okay, but we can't do the integral test yet. We have to first verify. So we first verify that we could make this f of x formula with no issue. And there is no issue. And it's continuous going from 2 to infinity. And it also needs to be positive. It's always positive. And it also needs to be decreasing. And we can see it definitely is decreasing because this only gets bigger. 1 is constant and this just gets bigger. So, all right, so we can do the integral test. And so what is the integral test? Well, you take this function that you made from the a sub n, this function of x, or a function of a continuous variable, and you do this integral, the integral from the starting point of the series to infinity of f of x. We need to evaluate this integral. And if this integral is convergent, this has nothing to do with like the ratio and root test is like they need to be, if it's equal to 1, it's inconclusive, greater than 1 type, stuff like that. No, the integral test If this is convergent at all, then the series is convergent. If this is divergent, then the series is divergent. That's the integral test. Okay, so we evaluate this improper integral by, we say the limit as t approaches infinity okay, and so we can make the substitution that u is natural log of x. So du is 1 over x dx. And so, okay, this integral, when x is equal to 2, u is equal to natural log of 2. When x is equal to t, u is equal to natural log of t. And we've got 1 over root u du. So u to the minus 1/2 du. All right, minus 1/2 plus 1 is 1/2. So it's u to the 1/2 over 1/2. So 2 root u. So 2, bring out the 2, root u evaluated from natural log of 2 to natural log of t. So we've got 2 square root of natural log of t minus square root of natural log of 2. So we can bring out that 2, the limit as t approaches infinity and we can see that this goes to infinity, which means it's divergent, so this is divergent. Okay, here we've got, they talk about when you're dealing with polynomials like this, you can think about doing a comparison test with a p-series where what you bring in to compare, so the b sub n, you take the order of the numerator and divide that by the order of the denominator. Okay, so you've got 1 over n. You bring that in for comparison, and even if you have, this is like under a square root or something, you can still think about if it was like this, you could still think about doing the same thing where the order of the numerator is 2 and the order of the denominator is 3/2. So this would be 2 minus 3/2. This would be n to the 1/2. Well, you wouldn't do it in this case because then the order of the numerator is greater than the order of the denominator, so that wouldn't converge. But for the problems they'll give, it would be the case where you'd get something negative, so it would be something over, like 1 over into some positive power, right? And if you had this, then this would be divergent. You just do the divergence test, but that's the idea. You end up with like something like n to the minus 1/2, so you have 1 over n to the 1/2, and that would be the p-series you would use to compare. Okay, but this, so I'm looking at this though, and so we've got 1 over n, and how is this related to n squared minus 1 over n cubed plus 1? So we've just taken off the minus 1 and the plus 1, right? This is n squared over n cubed, and this is kind of tricky because you subtract 1 from the numerator and add 1 to the denominator, and it's like it doesn't change anything, right? Okay, well, actually, no, this is not that tricky. Yeah, so if you subtract 1 from, okay, so so you take this and you subtract 1 from the numerator, that becomes smaller than this, right? And if you add 1 to the denominator, that becomes even smaller. So this is going to be less. Yeah, it's not as tricky as I thought it was going to be trickier, but okay. So, all right, now p is equal to 1. This is divergent. This is always greater. These terms are always greater than these terms. So that test is inconclusive. All right, so, okay, what about an integral test? So if we substitute, there's no issue there. Now, is this decreasing? Yeah, the x cube is going to dominate, going to take over. And you'll, as x gets larger, definitely this is decreasing, and it's continuous. So okay, we can do the integral test going from 1 to infinity. Okay, so actually before we do this, let's simplify this. So we've got the sum of two cubes here. Okay, the sum of two cubes, you do, it's going to be x plus 1, and then x squared minus ax, and then plus 1, right? Go look up the sum of two cubes formula. And then here we've got x plus 1, x minus 1, okay? So we've got x squared minus x plus 1. So that should make the integral a little bit easier. All right, so x squared minus x. Okay, so this is the limit as t approaches infinity. Okay, and so we know how to integrate this. This is, you know, if we know from the partial fraction decomposition, the integration of rational functions, this is a general term with a quadratic factor in the denominator. So we know how to integrate this. But this isn't about a video on integration. So what I'm going to do is let's just use the calculator. So going from 1 to infinity. Yeah, we had a whole lesson on how to integrate a term just like this. That's all in the integration of rational functions. So, okay, well, let's do x plus 1 over x squared minus x plus 1. Store that as e. Now we want to integrate from 1 to infinity of that e with respect to x. That is infinity. Therefore, this is divergent, according to the integral test. Okay, so when you see this minus 1 to the n, you know, the first thing you think is alternating series. However, you remember you need to be careful with that, with making that assumption right away, because for an alternating series, you need to be able to separate out like a minus 1 to the n or n minus 1 from a positive portion. And so we need to make sure that the hyperbolic cosine is going to be like always positive. Because like, for example, minus 1 to the n power like this over just sine of n. That would not be an alternating series. Okay, and we talked about why this is the case, but if we take a look at, there's hyperbolic cosine, that's always positive for all n. So this is an alternating series, right? You can write any alternating series, the sequence formula, as something like this. The alternating portion with a corresponding b sub n, where the b sub n is always positive. Well, here we can see that the b sub n is one over hyperbolic cosine of n. All right, so we know it's an alternating series. So what test do we use? Well, remember, anytime you have an alternating series, your first thought should be alternating series test. Now, that doesn't mean that the alternating series test is always going to work. Like we can use other tests to test alternating series, but still, like, that should be the first thing you consider if you have an alternating series, is the alternating series test. Okay, and so there is a requirement in an alternating series test. You can't use that test on any alternating series. It needs to be the case that the b sub n is always decreasing, for n is equal to 1 to infinity, or you know, some n to infinity. Well, again, if we look here, we can see it's cosine, hyperbolic cosine is just, it's always increasing. So that means this is going to be always decreasing. The b sub n needs to be always decreasing. I think I might have said increasing. B sub n, as n goes to infinity, b sub n needs to be decreasing. Like b sub n plus 1 needs to be less than b sub n. And so since hyperbolic cosine is always increasing, then that means 1 over hyperbolic cosine is going to be decreasing. So this is eligible for the alternating series test. Now, the alternating series test is you take the limit of the sequence. Well, no. You take the limit of the b sub n. The b sub n sequence. Well, we just saw this limit's going to be equal to 0. Okay, what the alternating series test says that if this limit is equal to 0, then this is the actual series is convergent. Okay, so when you see products of power terms like 2 to the sum n or 3 to the sum n, even k to the k, as well as factorials, like they're all being multiplied together. Either products of power terms, just factorials, or a mixture, then you think about the ratio test. So yeah, this looks like a typical ratio test type problem here. So, okay, the ratio test is you take the absolute value of a sub n plus 1 divided by a sub n. Okay, and so we don't need to think about all of these are going to be, there's no absolute value to think about here. This is always positive as k goes to infinity. So we can remove the absolute value, and then we've got, okay, 2 to the k plus 1 minus 1 is just 2 to the k, and then times 3 to the k plus 1 plus 1. All right. Now we know with these ratio test problems, we're going to end up canceling terms. So let's transform this 3 to the k plus 2 into 3 to the k times 3 squared. Okay, then k to the k plus 1, let's write that as k to the k times k to the 1. Now times, because we're going to take the reciprocal of a sub n because we're dividing them. So we've got k to the k in the numerator, and then, so let's do 2 to the k times 2 to the minus 1 times 3 to the k times 3 to the 1. Let's do that. So, okay, 3 to the k's cancel, the k to the k's cancel, the 2 to the k's cancel, and we've got, so this cancels. All right, so we're left with, so 3 times, we could bring 2 to the numerator, so 3 times 2 is 6. It's going to be 6 over k. All right, so then we take the limit as, well, okay, I don't know why I'm putting n here. This is k. Right, that's what you use for the constant in the, or for the variable in the sequence formula is arbitrary. It doesn't have to be n. So the limit as k approaches infinity of this a sub k plus 1 over a sub k, that's equal to 0. And for the ratio test and the root test, it's the same result, like the same criteria for the result. You see, is this limit less than 1? If it is, then that means that this is absolutely convergent, which means that this is convergent. This series is convergent. Okay, looking at this, if you notice, we can write it this way. We can say, so 1 plus n cubed over, or no, under n squared to the n power, right? And when we see something like this, we think root test for sure, 100%. What do you do with the root test? Well, you say, okay, the absolute value of a sub n, and that's not going to be, the absolute value is not going to come into play here. This is always positive. And then you take the nth root of that, all right? And so in that case, that's n squared over 1 plus n cubed. And then you just take the limit of that root of the absolute value. So we've got n squared over 1 plus n cubed, and we know this is going to be equal to 0. Remember from limits, we can see the order of the denominator is greater than the order of the numerator, so that means you're always, with a rational function, that means you're always going to have the going to infinity is going to be equal to 0. Okay? This is the same as the ratio test. We say that we look and see that this is less than 1. That means this is absolutely convergent, and thus that means it's convergent. Okay, I see this minus 1 to the n, and I think alternating series, but remember that's only you have to check further to make sure it's alternating. This is always positive. So this is like the b sub n. So this is an alternating series. So, okay, alternating series test. Let's think about that first. So the b sub n is natural log. Okay, this needs to be decreasing, all right, in order to apply the alternating series test. It's hard to tell just looking at this. So what we can do is, can we replace n with x and there's no issue? Yeah, that's fine. So let's take the derivative. All right, quotient rule, derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. All right, so root x over x is 1 over root x. Okay, so we can factor out a 1 over root x. All right, when does this equal 0? So when 1 over root x equals 0, and that it can't. That can never equal 0. So it's only going to be when 1 minus 1/2 natural log of x equals 0. If that happens, if that does ever equal 0. So you've got 1/2 natural log of x is equal to 1. Natural log of x is equal to 2. X is equal to e squared. So, okay, but so the derivative can change signs at x is equal to e squared, but maybe it changes sign to a positive sign, f prime. So that means it would be positive going all the way to infinity. So what we need to do is, okay, what is e squared? We could just take the limit as x goes to infinity of f prime of x, but it might be easier to just plug in something. Oh, wait, hold on. No. E squared, there we go. 7.3. Well, okay, well, no, hold on. What is natural log of, let's do e cubed. X is equal to e cubed. What is f prime of e cubed? So natural log of e cubed is 3. So, okay, you've got 1 over... So this is positive, this is positive, this is negative. So there we go. The second derivative is, or the first derivative is negative when x is greater than e squared, and it's not going to change signs after that. So the going all the way to infinity, this is the first derivative is negative. Therefore, this b sub n is decreasing as x goes to infinity. Okay, so now we just take the limit as n goes to infinity of that b sub n, and so this we can go back to find the limit of a sequence. In general, the most common method is you replace n with x if that's okay, if that doesn't cause any problems, and then these are going to have as long as there's no issues going from n to x, then these are going to have the same limit. All right, so as x goes to infinity, you have infinity over infinity. So let's use L'Hopital's rule. Okay, so, all right, what is... So this is 1 over 2 root x times x. X to the first divided by x to the 1/2 is x to the 1/2. So root x over 2. So, okay, we've got all right, as x goes to infinity, this goes to 0. And that's if this is the case, if this goes to 0, then that means this original series is convergent. Okay, same idea as the previous problem. Here, what we need to check, is this actually an alternating series? This is going to be always positive, so yes, this is an alternating series. Let's do the alternating series test. Okay, now is this decreasing? Let's see. Okay, so if we replace n with x, that's okay. Now, the limit as x goes to infinity of, that's infinity over infinity, so L'Hopital's rule, 4x cubed over 4 to the x natural log of 4. Okay, and so that is 4 over natural log of 4, limit as x goes to infinity of x cubed over 4 to the x. That's infinity over infinity, so if you do L'Hopital's rule again, we'll get 3x squared over 4 to the x natural log of 4. So, okay, what we've got there is, bring those constants out. You've got 12 over natural log of 4 squared, limit as x approaches infinity of x squared over 4 to the x. Once again, we've got infinity over infinity. L'Hopital's rule again, so we're going to have 12 times 2 is 24 over the natural log of 4 cubed. And then we've got x over 4 to the x. That's infinity over infinity again, L'Hopital's rule. So we've got, this is going to be just 1, and then this will be 4 to the x natural log of 4. So we've got 24 over natural log of 4 to the 4th, limit as x approaches infinity of 1 over 4 to the x. And that is equal to, that goes to 0. Now, okay, why did I just do that right at that step? I should have checked first that this was decreasing. That's what I meant to do. Okay, so it still should be okay because, okay, if this is decreasing, then what I just did was I found the limit of b sub n and got 0. So if this is decreasing, then that means that this passes the alternating series test and this is convergent. If this is not decreasing, then this was all a waste of time. So we can determine if it's decreasing by taking f prime of x. So derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. So, okay, let me make some room here. All right, when does the numerator equal 0? All right, so we've got 4x cubed, 4 to the x, minus 4 to the x, x to the 4th, natural log of 4 is equal to 0. Let's take out a 4x cubed. No. Let's take out a 4 to the x, x cubed. So you've got 4 minus x natural log of 4. Okay, this is equal to 0 when x is equal to 0. Okay, and when is this equal to 0? So when is x natural log of 4 equal to 4? When x is equal to 4 over natural log of 4. So 4 over 2 natural log of 2. Okay, and this is greater than 0. So we need to find out what is the sign of the first derivative for any x value that's greater than this. Or we can just think about what is the limit as x goes to infinity of this. So yeah, the limit as x goes to infinity of this here, you've got 4 to the x is positive infinity, x cubed is positive infinity, so this is infinity. Here you get 4 minus positive infinity, so you have times minus negative. So, okay, yeah. The limit as x approaches infinity of f prime of x, well, okay, then the denominator here is positive infinity, is going to be negative infinity. So okay, that means this is decreasing. So therefore, we saw that the limit of this is 0, so this is convergent. All right, so you see everything, this entire a sub n is to the power of n, and the first thought that you think about in that case is the root test. So the nth root of the absolute value of a sub n, do we have okay, so is this ever negative? So let's look at the graph. All right, here is 2 to the 1 over x minus 1. So going from when x is positive all the way to infinity, it looks like it's never negative. It's like it approaches 0 from the top. So as far as the absolute value goes, we don't need to think about the absolute value. So that means that this is just equal to that. Okay, now the limit for the root test, we take the limit as n approaches infinity of this, which we saw is going to be 0, should be 0. Okay, yeah, so what you're doing, so, okay, if we think about this as a function, so f of x is equal to, well, let's just look at the xth root of 2, so 2 to the 1 over x. You're just taking a higher and higher root, right? The 50th root. So this is just going to get smaller and smaller and smaller, and it's going to approach. It'll approach 1 from the top, right? Because you once you get to 1 or below 1, you can't. There's nothing you can multiply together, however many times, and get 2, right? But if 1.1, you could multiply that a certain amount of times, or like something in that range to get 2. Right, not 1.1, but something in that range. You could multiply that a certain amount of times to get 2. Anything above 1, you could find some number that's really close to 1 that could multiply a certain number of times to get 2. But once you get to 1, so this is going to be approaching 1 as x goes to infinity. So 1 minus 1 is 0. This is less than 1, so by the root test, this is absolutely convergent and thus convergent. Okay, so here I'm thinking a comparison test, because we can, when you look at this, what you can think about is that we can come up with a geometric series that closely resembles this, but the idea is we want to come up with a geometric series. So let's take off the 4 to the k. So we have 5 to the k over 3 to the k is 5 over 3 to the k. This as a geometric series is divergent because the 5/3 is greater than 1. Okay, but that's fine, right? But the reason why we want to use the comparison test is because all we had to do to get this geometric series here was take off this 4 to the k. So there's going to be a relation, a greater than, always greater than, or always less than relation between the sequence we're studying or the series we're studying and this one. So since as 4 to the k is positive increasing. So the denominator is always going to be, as k goes to infinity, the denominator will always be bigger than this denominator. So this is always going to be less than this. Okay, but 5/3 to the k is divergent, so the test is inconclusive because this is greater than this. Okay, so what about the ratio test? I'm not sure. So this is always positive. So we don't have to worry about the absolute value. So you've got 5 to the k plus 1, which is 5 to the k times 5 to the 1. Then 3 to the k plus 1. Let's write it. Okay, 3 to the k times 3 to the 1 plus 4 to the k times 4 to the 1, but there's not going to be any canceling. Okay, then we've got 3 to the k plus 4 to the k over 5 to the k. So, all right. So you've got 5 times 3 to the k plus 4 to the k. And then actually, let's go back. I think it'll be it'll be easier to compare this way. All right. And so can we take the limit as k approaches infinity of this? We could take out the 5. Well, yeah, okay, this is going to go to 0. You have the exact same, the numerator and denominator are the same, except like you're adding this term is always going to be bigger than this term. This term is always going to be bigger than this term. So the sum of these two terms is always going to be less than the sum of these two terms. But does that mean that it goes to 0? Well, okay, no. Okay. That doesn't tell us that it necessarily, that doesn't prove 100% that it goes to 0, but it does prove something. It proves that, well, okay, let's focus on, let's take this 5 out, okay? So just looking at this limit is going to be less than 1, for sure. But when you think about multiplying by 5, then that doesn't help you. This would be very useful if we didn't have this 5 here, because then we'd say it's convergent, but we need to know how much less than 1, because if it's just a little bit less than 1, then we could have 5 times that is greater than 1. If it's a lot less than 1, then we could have 5 times that number is less than 1. What we really need to know is this less than 1/5? Okay, so let's see, let's come back here and see what we can, if we can rearrange this. Okay, let's factor out a 4 to the k. And then you've got 3 to the k divided by 4 to the k plus 1. And then if we factor out a 4 to the k plus 1, you've got 3 to the k plus 1 over 4 to the k plus 1 plus 1. Okay, and so what you've got is, so, okay, this is 4 to the k times 4, right? Or 4 times 4 to the k. So 4 times 4 to the k. There we go. So we've got 5/4 times 1 to the k. Yeah, there we go. Times 1 to the k, which is just 1. So yeah, these cancel. And then we've got times, so 3 over 4 to the k plus 1 over 3 over 4 to the k plus 1 plus 1. All right, so what is if we have 5/4, the limit as n goes to infinity okay, as n goes to infinity, this goes to 0 and this goes to 0. So this goes to 5/4, which is greater than 1, which means this diverges. Okay, here we could, looks like we could do the ratio test or the integral test. You know, because, okay, this is, let's do the integral test, because we get a lot of practice with the ratio test, I think. So we can, if we replace, can we replace n with x, and there's no issue. That's fine. Okay, is this decreasing? Yeah, I'm not even going to test this, because you could argue that e to the x itself is increasing faster than x squared is. Definitely e to the x cubed. So this is decreasing. But I mean, you know, if you were doing like if this is like a project you were working on, or you know, you want to officially test it, right? But I mean, I think it's a good educated guess for the purposes of this video to say this is decreasing. So, I mean, okay, well, let me use the calculator. There we go. X squared divided by e to the x cubed. Store that as e. Oh, wait. There we go. Okay. All right. What is the derivative Okay, now let's store this as e. And now we want to solve for when e is equal to 0 for x. X is equal to 0 or x is equal to this value, which is a positive value. So let's just, okay, well, what is this? .87. So let's just take the derivative and plug in. Where's the derivative? We stored that as e. Plug in 1, or we can plug in whatever we want. But yeah, let's do 1. So e with x is equal to 1. It's negative. And that sign's never going to change. So there you go. It's always, this is decreasing as x goes to infinity. So, all right, going from 1 to infinity, right? We start at 1. What is this improper integral? So we take the limit this is e to the x cubed. Okay, so if we just come to the side and do this, so we see we can make the substitution that u is equal to x cubed, therefore 1/2 du is equal to x squared dx. All right, when x is equal to 1, u is equal to 1. When x is equal to t, u is equal to t cubed. And we can take out that 1/2, and we've got 1 over e to the u. So e to the minus u du. So 1/2, the integral of e to the minus u is minus e to the minus u. So take out that minus, and you've got e to the minus u. So e to the minus t cubed minus e to the minus 1. Okay, so we could take out the minus 1/2, and we've got the limit as t approaches infinity of and so this limit, this goes to 0, and so this limit goes to 1 over 2e, and that this means it's convergent. It converges, so this is convergent. Okay, so I look at this and I notice that you can rewrite it as a power of n. And in that case, we want to do the root test. So n factorial over n to the 4th is always positive, so that means this is going to be n factorial over n to the 4th. Now all we need to do is take the limit as n approaches infinity of n factorial over n to the 4th. Okay, so we know that, I don't know if this is going to help, but we can't think about L'Hopital's rule here with the factorial. But this is n times n minus 1 factorial, right? Or no, over n to the 4th. So I'm not sure if that helps us. I guess it simplifies it a little bit. But remember, with the ratio and root test, we're not trying to see, we just need to see if this is like less than or greater than 1. So we're not constrained to find a specific value. So can we show that for sure this could never be equal to 1? It has to be less than 1. In fact, I think that'd be easier. Let's go back to the original form. I think it'd be easier to visualize. And just n factorial over n to the 4th. All right, so we've got, so n times n minus 1 times n minus 2 times 3 times 2 times 1 over n times n times n times n. Okay, let's do this. Let's try a number here. So if we have n is equal to 5, we've got 5 times 4 times 3 times 2, and then we've got 5 times 5 times 5 times 5. All right. So this is, like we simplified, to 4 times 3 times 2 over 5 times 5 times 5. That's n minus 1 factorial over n cubed. Okay, well there you go. So yeah, so we should have left it that way. This tells us that yeah, like here, when you think about, if you multiply like n minus 1 times n minus 2 times n minus 3, all, you're going to have like a n minus 1th order polynomial, right? And this will be 1 order higher every time. So in that case, this could never be equal to or greater than 1. And then here you could see as well, just like this doesn't prove it, but like this, you could never overtake, like you're always going to be multiplying 3 terms here if you left out the 1, and 3 terms down here, but you can see this will always be bigger than this. Now, does this limit go to 0? Does this limit go to 0.2? We don't know, but it's for sure going to be less than 1. Well, okay, but you might say, well, what if it's negative infinity? Well, okay, well, it's actually going to be between. All right, we can say this. It's going to be, okay, so greater than or equal to 0 and less than 1. Maybe this limit is 0. But it's not going to be less than 0, right? How can it be less than 0? This is never negative. This is never negative. So with this tells us here is that it's equal to something. It's not going to oscillate, right? How would it oscillate? So that means that since this is equal to, this is convergent, and it converges to something that's less than 1, then that means that this is absolutely convergent, which means that this is convergent. Well, this is absolutely convergent, which means it's convergent. Okay, here, remember we can separate this into 2 separate sums. Okay, and analyze these separately. If either one of these is divergent, then this entire sum is divergent. And if both are convergent, then the entire sum is convergent, right? Because remember, if this is convergent, then that means this is equal to a value, a finite value. And same thing here. If this is convergent, that means this is equal to a finite value. Well, a finite value plus a finite value is another finite value. Okay, this is a p series with p is greater than 1. This is convergent. This is a geometric series with r equal to 1/3, less than 1, or the absolute value that is less than 1. That's convergent. So this is convergent. We're just adding a p series with p greater than 1 and a geometric series with the absolute value of the common ratio less than 1. All right, here, this one's kind of tricky, but just remember with comparison tests, they're very flexible. Like you might say, oh, we can't do a comparison test. We have to, there's too much to take off here. Don't think about it like that. Like we could say, okay, we take out the 1, take out the natural log of k. We're left with k over k cubed. Right, so that's 1 over k squared. All right, now how does that, this is the only issue with the fact that we had to take off so much stuff to create this p series is that there's less of a chance that we're going to be able to say that this is always less than or greater than this. That's the only issue. Okay, so let me write this. And in this case, that might be an issue. So, okay, we took off the natural log of k. And so that would, and that if that was the only thing we took off, then we would have, this would be the relation. But we don't know, because adding this 1 here makes this, it raises this. Well, oh no, okay, we're good. Yeah, it makes the denominator smaller, which makes the ratio bigger. So the natural log of k and the +1 make this bigger, so this is always greater. Let's see if we can get a comparison test to finally work for once. No, it's not going to work, because this is convergent, and this is always less than this. So it doesn't tell us anything. If it was the other way around, then it would work. We haven't had one comparison test work yet. Okay, so I'm thinking about the integral test, and the only reason I'm shying away from it is because this is such a long video already, and that could take a lot of work to compute everything. But if you agree with me that we're going to use the calculator here for the integral test, and as we go, just take note that there's nothing I'm going to be doing that we couldn't do on our own, and understand exactly what we're doing. That's when it's okay to use a calculator, unless you're doing a problem that's directly related to like if we were just because you know what you're doing, but you're doing a problem that tells you to take a derivative. Well, then no, don't use the calculator, because the problem is about derivatives. But if you're doing a problem and it's not directly about derivatives or something like that, that's something from another subject, then you can consider using a calculator if you're sure that you know exactly what you're just doing it to not have to go through all the labor, right? So, okay. Well, all right. If the integral test, we replace the k with x, and is there no issue there? That's step 1. We're good. No problem. All right. Now, is this decreasing is the next question. So, all right, x times natural log of x divided by x plus 1 cubed. There we go. Store that as e. Okay. Now we want to take the derivative of e with what? Yeah, there we go. So, and we're going to store this as d. Now, what are they telling us here? Oh, that should just telling us like you can't yeah, you might get a derivative where like any derivative is, even if you evaluate a derivative and it has a certain domain that like, let's say you could plug in 1 to the derivative and get a number, but you go back to the original function and you can't plug in 1. Well, then 1 is outside of the domain of the derivative, even though you actually get a number when you plug it into the derivative. So that's just warning us about that. But we're fine. That's not an issue for this. All right, so there's the derivative. Now we want to solve for when d, the derivative, is equal to 0 for x. All right. So now what we want to do is we want to plug in something into the derivative function that's greater than this. So let's plug in 3. What is the derivative with x is equal to 3? And what is that? Is that positive or negative? That's negative. So like we could plug in anything now into the derivative and it's always greater than 3, it's going to be negative. See? So we know that this is decreasing. Since this is decreasing, that means this is decreasing. And also, okay, but it needs to also be positive and continuous. It's positive and continuous going from 1 to infinity. Okay. So now we need to take the improper integral from 1 to infinity of x natural log of x over x plus 1 cubed dx. And we're going to use the calculator again. So we've got improper integral from 1 to infinity of, and this is the original function e, not the derivative, and that's convergent. And we don't care about what this converges to, remember, with the integral test, so that means this is convergent. Okay, so looking at this, this is an alternating series. This is always positive as n goes to infinity, and so there we go. So we've got this. This is the b sub n alternating series. So let's consider alternating series test, and we just had this without as not an alternating series. So b sub n is equal to n squared minus 1 over n cubed plus 1. We evaluated this as a series alone earlier, right? And so this b sub n is decreasing, right? And we could verify that real quick. So x squared minus 1 over x cubed plus 1, and then the derivative, we'll store that. Oh, come on. Store that as d. Okay, now, well, okay, it's at x is equal to 0 and x is equal to 2. It's the derivative is equal to 0, so let's just plug in, you know, d, just plug in any number greater than 2 with x is equal to just 1,000, whatever. It's negative, so there you go. So it's decreasing, so the alternating series test, we take the limit as n goes to infinity, and this is going to be equal to 0, which that passes the alternating series test, so this is convergent. Now, the problem we worked earlier, when we just had this as a non-alternating series, that was divergent. And so, just to note, this is conditionally convergent. Right? The absolute value series is not convergent, but this is. It's like the harmonic series. Okay, here, this reminds me, if you think back to the limits chapter, we looked at like the limit as x approaches 0 of sine of 1 over x. And that one was tricky because it ended up being like an oscillating discontinuity. You know, if we look at the graph of tangent of 1 over x, right, as you approach 0, it's oscillating, but we're going to infinity here, and so it makes sense that as n goes to infinity, 1 over infinity approaches 0, tangent of 0 is 0, and it looks like as x goes to infinity, tangent of 1 over x is approaching 0. Okay, so the test for divergence doesn't tell us anything, and so, you know, we don't want to do the ratio test. Let's look at the integral test. So can we do this? And there's no issue. Just replace n with an x. That looks to be fine. All right, is this decreasing? Yeah, we just saw the graph, and we can look at this and tell that it's decreasing as x goes to infinity. So we just need to evaluate from 1 to infinity. So let's just go ahead and use our calculator here. There's no need to go through the drawn-out integration process. So infinity. So that means that this according to the integral test, this is divergent. Okay, looking at this, you know, I see that we could separate this into n to the first times n to the 1 over n. So maybe the ratio test, or maybe a comparison test, because that's, yeah, let's do that. So we can write this as so n times n to the 1 over n, right? And we can compare this to 1 over n, the series 1 over n, so which we know is divergent. And so how is these terms related to, is this always greater than or less than, you know, these two? Is one always greater than or less than the other? So n to the 1 over n. So as n gets bigger and bigger, this is getting smaller and smaller and smaller. So it's like, you know, 3 to the 1/3, then 4 to the 1/4, then 5 to the 1/5. Let's take a look at a graph of x to the 1 over x. Okay, yeah, so this looks like it has a horizontal asymptote of 1 maybe, or maybe it's I don't know, but it looks like it's always decreasing as x goes to infinity. But we want to verify this officially. So, you know, if it's the case that this is always decreasing, then that means we'll have this, right? But okay. All right. F prime x is equal to, you know, because if this was like 2 to the 1 over x, then yeah, it's definitely decreasing. But with this x here, it's kind of, you know, yeah, this is decreasing, but the x is getting bigger too. So it's hard to say for sure just looking at it. So, all right, chain rule, or wait, no, we can't do, we need to do, yeah, logarithmic differentiation here. So, okay. Y is equal to x to the 1 over x. Take the natural log of both sides. So natural log of y is equal to the natural log of x to the 1 over x. So natural log of y is equal to 1 over x, natural log of x. So now take the derivative of the entire equation with respect to x. So we've got 1 over y prime is equal to, all right, product rule, the derivative of the first times the second plus the derivative of the second times the first is that. So we've got 1 over y prime is equal to 1 over x squared, 1 minus natural log of x. So y prime, if we multiply both sides by y, so we've got x to the 1 over x over x squared, 1 minus natural log of x. So there's the derivative. Now, as x goes to infinity, what do we get? You know, or just think about plugging in a big number. So this will be negative, 1 minus natural log of, you know, anything, a big number. And then a big number, this is always positive, so there you go. That the derivative is negative. Going, you know, away towards infinity. So this is decreasing. The n to the 1 over n is decreasing, which means that this is decreasing, so this is greater than that. Now this is divergent, this series, and so that now we've got our first comparison test that's finally worked. That means this is divergent, or yeah, that means this series is divergent. Well, that's this series, so divergent. Okay, I see this minus 1 to the n. I think the alternating series test, but remember we need to verify that it is in fact an alternating series. Like this it might not be because of this cosine term here, but as n gets larger and larger, this is just approaching 0. Or no, this is approaching, it's approaching 0 from above. So if we think about the unit circle, it's approaching, coming to 0 here, and the cosine of 0 is 1. But it's always going to be positive, though. It'll be coming, cosine will be coming from below 1 as n goes to infinity. So this is an alternating series. This is like the b sub n. So it's an alternating series with the b sub n is okay, so alternating series test. Okay, well, first step, we have to verify that b sub n is decreasing. We know it's positive. Okay, but it is decreasing. We just talked about that. It is decreasing. So now we just take the limit as n approaches infinity of the b sub n. Well, we just talked about that's equal to 0, and that means by the alternating series test, this series is convergent. Oh, wait, no, I'm sorry. This limit was equal to 1. This limit was equal to 1, which is not equal to 0. Therefore, this series is divergent. Okay, here, I recognize this should be perfect for just testing for absolute convergence. Because, okay, we notice that we can create a geometric series here with 1 over 2 to the n. So that's 1/2 to the n. A convergent geometric series, right? The absolute value of the common ratio is less than 1. All right. And so what we're going to do, though, is, so as n goes to infinity, sine of 2n is oscillating between -1 and 1, which usually complicates things with regards to the comparison test. But we can, if we think about the absolute value of this, then like the series, like this series, the series, and so the absolute value of sine of 2n over 1 plus 2n, but 1 plus 2n is always positive, so right, if we determine that this is convergent, then that means this is convergent. That's the idea with absolute convergence. It's nice. You could always, well, if I look at the absolute value series and I figure out that that's convergent, well, then I've determined that the original series is convergent. And so, okay, with that, what we have is the absolute value of sine of 2n over 1 plus 2n, right? And we can, this is also 1 over 2 to the n is the absolute, we can take this from the absolute value of, like this is always positive, so we don't have to think about an absolute value is what I'm saying. So, all right, so in that case, okay, well, what's the difference? So, okay, we changed this to, this is 1 over 2 to the n, right? So we took out a 1 from the denominator. So if we had sine of 2n over 2n, the absolute value of sine of 2n over 2 to the n, then that would mean that this is always less than this, okay? Now here, at most, we're adding 1 to the numerator. In fact, I only, because n is an integer, I don't think we'll ever add 1. Sine of 2n integer will never be 1. So this would be something between 0 and 1. I don't think it would be 0, ever be 0 either because of the integer. But remember, we're really flexible when it comes to the comparison series. And so we can say, let's just bring in 5 over 2 to the n. Well, no, we can't do that. Okay, we could do, what, 3/2? Yeah, 1.5 over 2 to the n. Right? And that's just absolutely valid because you just take the 1.5 out of the summation. So we're going to bring in 1.5 over 2 to the n. And now with that, we can see that. So removing the 1 from the denominator is going to make this bigger. Well, actually, we didn't even need to do that because, okay, yeah, if we think about it, if we come back here, removing the 1 from the denominator made this bigger. Now, okay, so if all things were equal, we'd automatically have a bigger, this would be bigger than this if we had an absolute value sine of 2n in the numerator. But, okay, we don't have a sine of 2n, but sine of 2n, the absolute value is never going to be bigger than this, right? So that means this is definitely going to be bigger. You see? If we remove the 1 and this was bigger automatically, then the only way this could potentially be bigger or equal to is that we'd need the numerator to make up for the difference. But it's not going to, because the absolute value of sine of 2n is always less than 1, or it could be equal. I don't even think it's equal. Even if it was equal, potentially, it wouldn't matter. Okay, so here's the inequality. Now, this is convergent, and this is greater than this, the terms, so that we have another comparison test that worked. That means this is convergent. Okay, looking at this, I think about an integral because the derivative of 1 over n is 1 over n squared. And so, you know, we can evaluate the integral easily here. So let's look at the integral test. All right, so that's fine. That's valid. There's no issues with going from n to x. Now, is this decreasing? Yeah, it should be, because if you think about f prime of x is going to be what? E to the 1 over x times minus 1 over x squared. Okay, yeah, the derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. So we've got minus e to the 1 over x minus 2x e to the 1 over x to the 4th. So minus, well, let's take out a, okay, minus e to the 1 over x, 2x plus 1. And yeah, I mean, okay, yeah, that's always negative. Okay, it is decreasing. All right, so now we go from 1 to infinity, the integral test, e to the 1 over x squared. And we could do this integral. This is an easy integral. So the limit as t approaches to infinity, all right, so coming off to the side and doing this, if we say u is equal to 1 over x, then du is equal to minus 1 over x squared dx. So bring out that minus. When u is equal, or when x is equal to 1, u is equal to 1. When x is equal to t, u is equal to 1 over t. And then we've got e to the u du. But then we brought out the minus sign. So, all right, minus, and then e to the u evaluated from 1 to 1 over t minus e to the 1 over t minus e. So this is e minus e to the 1 over t. So the limit as t approaches infinity of e minus e to the 1 over t. As t goes to infinity, we have e to the 0. So this is e minus 1. That's convergent. That converges to something, so that means this is convergent. Okay, remember, we can always start by we could look at the a sub n and think about what is the limit as n goes to infinity. And in this case, we can see that's going to be 0. So that's the test for divergence doesn't tell us anything. But if we saw that this was, so like, let's say this was just n plus 1, n to the first plus 1. Well, that limit would go to 1. That's not 0, so we know it's divergent. So you can always start with the test for divergence. Just take a glance at the a sub n. All right, but this is going to be we're going to take a comparison test, right? So b sub n is equal to n over n cubed, which is 1 over n squared. So how does that compare to the sequence. So, all right, we subtracted, we took out a -1 here and a +1 here. So what does that mean? Well, if you add 1 to the denominator, that makes it the term smaller. And if you subtract 1 from the numerator, that makes the term smaller. So this is going to be greater for all n, right? Because this is n over n cubed. So this is divergent. So the test is inconclusive. Okay. Maybe the ratio test. Yeah, let's try the ratio test. Well, no. Ratio test, this doesn't work for... If we did the ratio test, then the limit would be equal to 1. It would be inconclusive for expressions like this, like rational expressions or like those algebraic expressions with the... It's like a rational expression. Well, it's not a rational expression. It's a fraction with like roots. Like if you had this, you know, we could do like a comparison test with this, but this, if you did the ratio test, it would, the resulting limit of a sub n plus 1 over a sub n would be equal to 1. All right. As far as like an absolute value, like test for absolute convergence, that's not applicable here because it doesn't help us to take an absolute value. So, I mean, let's do the integral test. So if we replace n with x, is that an issue? No. Okay. Yeah, so we've got if we can factor this, but actually that's not going to help us cancel anything. Yeah, I mean, we could use our calculator to get the integral. So is this always decreasing? So let's go ahead and get the derivative. Derivative of the top is 1 times the bottom minus derivative of the bottom. It's 3x squared. So, okay. Times the top all over the bottom squared. So we've got x cubed plus 1 minus 3x cubed plus 3x squared. Okay, so we've got minus 2x cubed plus 3x squared plus 1. When is this equal to 0? So, I mean, okay, this is going to take too long. We have to solve this polynomial equation. So let's just use our calculator. All right, so x minus 1 divided by x cubed plus 1. Store that as e. All right, now the derivative of this with respect to x is, we'll store that as d for derivative. All right, when is the derivative equal to 0 for what values of x? That value. So let's plug in x is equal to 2 into the derivative. And hopefully it's negative. It is negative, so this is decreasing. All right, so now what is it's continuous, positive, and decreasing. So it's eligible for the integral test. So now what is this integral convergent or divergent? So the integral from 1 to infinity, it's convergent to third natural log of 2. But I didn't even have to write this because remember, this doesn't matter. So this is convergent. Okay, here I think the ratio test, because the strategy that we talked about was that if you have products of exponentials like this and with factorials mixed in, then that's great for the ratio test. So this is a classic ratio test problem here. All right, so the absolute value of a sub n plus 1 over a sub n. We don't have to worry about the absolute value. So 3 to the n plus 1, let's go ahead and separate that into 3 to the n times 3 to the 1. N plus 1 squared. All right, now n plus 1 factorial, let's write that as n plus 1 times n factorial, because that's going to cancel with this, n factorial. And then 3 to the n times n squared. So, okay. So we've got 3 times n plus 1 over n squared. All right, now what is the limit? As n approaches infinity, we can take out that 3 of n plus 1 over n squared. This goes to 0, and so that means this is equal to 0, which is less than 1, which according to the ratio test means this is convergent. Okay, so I'm thinking we can use a bit of an unconventional comparison test here. So sine of k is, well, actually let's do this. Let's do the absolute value. Let's test for absolute convergence. So if we think about the absolute value of this, what that would mean is, well, no, that wouldn't work. So 2 plus sine of k is going to be, we're assuming that sine of k oscillates between -1 and 1, but it actually probably won't do that when we're thinking about just integers. But let's just, in general, think about it that way. So this is, the denominator is going to go from 1 to 3, which is always positive anyway. So this is always positive, okay? But if we think about, all right, and we can compare this to, so compare this to 1, right? And this is always going to be, or no, okay, no, that's not right. This would be, yeah, we can compare this to 1. This is going to oscillate between 1 and 3, but if you think about, so sine of k, sine of 1, sine of 2, sine of 3, for sine to be -1 or 1, so sine of -1 is, sine of pi over 2 is equal to 1, and sine of 3 pi over 2 is equal to -1. So that's what I'm saying. If all you've got is integers, you're never going to get to 1 or -1, right? So you can say that the denominator here is going to be always, as n goes to, or as k goes to infinity, it's always going to be between 1 and, this will be between 1 and 3. Right? You put that here. You see? Because you're never going to do 2 minus exactly 1, and you're never going to do 2 plus exactly 1. And so this entire expression is going to be, so it would be, let's see, less than 1/2, greater than 1/3. It's going to be between 1/2 and 1/3. And so what we can say is, let's think about the series. Let's do this. The series 1/5. This is going to be greater than 1/5 always, right? You might be saying the series 1/5, what is that? Well, think about it. What is this? You're just adding 1/5 plus 1/5 plus 1/5 infinitely many times. This is divergent. Well, since this is divergent and this is less, this is always greater than this for every single term, well, then this is divergent according to the comparison test. All right, I see this -1 to the n-1 term, and I think alternating series test, but let's make sure that it is actually an alternating series, and it looks like it is because this is always positive. Particularly as n goes to infinity, right? This is always positive. So, okay, alternating series test. You first need to verify that b sub n is decreasing, and it is. So now we just take the limit as n goes to infinity of the b sub n. We can see that this is equal to 0, so this is convergent, according to the alternating series test. Okay, this is what the textbook called like an algebraic expression. It's like a fraction that contains polynomials or radicals of polynomials. And so what you do is the b sub n you bring in for comparison is the order of the numerator, which in this case is 1, divided by the order of the denominator. So that's the square root of 2 is 1, so the order, it's k squared. So 1 over k squared, how does that compare to the a sub n here? So what we did, if you notice, all we did, it's kind of confusing, but the only difference between this and this is you took this 1 off. Right? Because think about it. Take the 1 off, what happens? You get the square root of k squared is k. K times k is k squared. Right? And that's why this works. So this is always going to be, you're going to have that. Right? Because you're always going to have this plus 1 in the numerator. It's the exact same thing, except you have this denominator is a little bit bigger, no matter what. So you have a smaller number. Okay? P series, this is convergent, but this is always greater. These terms are always greater than these terms are always greater than these terms. So this, by the comparison test, this is convergent. Okay, same type of problem as before. We've got, like, they call it an algebraic expression. It involves this, like, it's like a ratio of roots of polynomials or just polynomials. And I'm saying ratio. It's not like if you just had the cube root of k minus 1, that wouldn't be an algebraic expression. But then that's going to diverge, right? If you had just one of these algebraic expressions that weren't in a fraction, what's going to diverge? So there's only certain, the types of series that potentially converge are going to be like ratios most of the time, right? Because that's what creates the convergence. It converges to like a value because of the ratio. All right, so the b sub n we bring in, take the order of the numerator and divide that by the order of the denominator. So k to the 1/2 times k to the 1st is k to the 3/2. So 1/3 minus 3/2 is, so we've got 2/6 minus 9/6 minus 7/6. So there we go. So this is a P series that converges. P is greater than 1. How does this compare to the original a sub n? This looks like it's can be kind of confusing to see what we did, what we changed. So, oh no, not really, because yeah, we took the 1 and the minus 1 off. That's it. And so if that means that the numerator is always a little bit smaller no matter what than this numerator is always a little bit smaller than this numerator. And then when you're adding 1, that means this is always going to be a little bigger than the denominator, but that also makes the whole thing smaller. So we got this. This is a convergent P series. It's always greater, so this is convergent. All right, this is kind of an unconventional looking a sub n, but let's do the ratio test here. This looks, when you think about all these terms canceling, and it seems perfect for the ratio test. So, all right, there's no issue with the absolute value. Like we don't have to consider the absolute value. So, all right, we're going to have, so, okay, n plus 1, you have 2 times n plus 1 minus 1. That's 2n plus 2 minus 1. So 2n plus 1. So we've got 1 times 3 times 5, 2n plus 1 over, and then so 3 times n plus 1 minus 1, 3n plus 3 minus 1, it's 3n plus 2. So let me... All right, so 2 times 5 times 8, 3n plus 2. All right, now we've got 2 times 5 times 8, 3n minus 1, and then 1 times 3 times 5, 2n minus 1. Okay. So what we can do is we can rewrite this like, okay, 1 times 3 times 5, and then times what? Times 2n minus 1 times 2n times 2n plus 1, right? Same, that's the exact same thing. And we've got 2 times 5 times 8, and then we've got 3n minus 1, 3n, 3n plus 1, 3n plus 2. Exact same. These two are the exact same. Times 2 times 5 times 8. No. Wait. Yeah, that's right. Okay. Okay, and so now we see that all of this cancels. And all of this cancels. And so what we're left with is 2n, and then right? So now what is the limit as n goes to infinity of this a sub n plus 1 over a sub n? Well, we don't need to expand this out because we can see the order of the numerator is going to be one less than the order of the denominator. So this is going to be 0. That's less than 1, so this is, according to the ratio test, this is convergent. It's absolutely convergent, which makes it convergent. All right, I see this minus 1 to the n, and I think alternating series test. Is this an alternating series? Yeah, this is always positive. So the b sub n is pi to the 2n over 2n factorial. Now, this might not work. This doesn't mean the alternating series test is going to work just because we have an alternating series. All right, is this decreasing? You know, this might be kind of a pain to do. I don't know how we're going to verify that this is decreasing. I mean, we could. We just let's do the ratio test, because ratio tests can be nice for alternating series because of that absolute value. So right, we just take this out. So we've got what? Pi to the 2n plus 1 is pi to the 2n times pi. All right, and then 2 times n plus 1 factorial is what? That's 2n plus 2 factorial. And so what we want to do is 2n plus 2 factorial, we want to write it this way. 2n plus 2, 2n plus 1, and then 2n factorial. Because we're going to cancel that 2n factorial. You see that? That's 2n plus 2 factorial, right? So then we've got pi to the 2n, and then, okay. So yeah, this should work really well. Okay. So the limit as n goes to infinity is equal to, we can see it's 0. That's less than 1, so this is convergent. So yeah, there's a good example. That's a great example of how just because you have an alternating series, it doesn't mean that the best test is going to be the alternating series test, but that's just the first one you think about. And then as we got into it, we probably could have figured it out that this was decreasing. And then in that case, I mean, no, then the limit would have been a pain too, because I mean, I bet you we could have figured it out with the alternating series test, but it would have been a lot of labor compared to this, which was quick. You know, when it comes to factorials are great for the ratio test because you can get rid of the factorial with the ratio. But factorials are a pain with limits because it's hard to, when it comes to, like, if you're taking the limit of a sequence, a lot of times you want to convert that to a continuous function, and you can't do that with a factorial. So any of the methods that involve converting to a continuous function, and when do we do that? We do that a lot when we need to potentially take the derivative to verify that it's decreasing, or for the integral test, we need to convert it to a function of x, so we can integrate. Those are the situations where we potentially replace the n with an x. Okay, we worked a similar problem to this earlier, but there was a difference. So we're not working the same problem twice. All right, so what we saw was that this here, root 2, as n goes to infinity, the nth root of 2 approaches 1. So if we think about taking the test for divergence, the limit of this sequence is 0, so the test for divergence doesn't tell us that doesn't tell us anything. All right, so the ratio test or the root test doesn't seem like it would be helpful here. Absolute value test, this is always positive because this is always greater than 1. So let's think about the integral test. That's fine, that's no problem. Okay, let's use our calculator here. So we've got 2 to the 1 over x minus 1, store that as e. Now let's take the derivative with respect to x of e and store that as d. Okay, now let's solve for when d is equal to 0, for what x values is d equal to 0? It never is. And okay, but we can see that d then for any x is always negative. So this is decreasing, it's positive, decreasing, and continuous. So we can use the integral test if we're able to evaluate this integral. And so the integral from 1 to infinity of the original function e is infinity. This integral diverges, so according to the integral test, this series is divergent. Okay, here we're going to do the root test. So the absolute value of a sub n, the nth root, here that's going to be, so this is always positive, so we're going to have n plus 1. Okay, so what is the limit as n approaches infinity of this? Okay, well, what is as n approaches infinity, what does this approach? 1. But 1 to the infinity is an indeterminate form. So we could plug this into our calculator, but I guess let's go ahead and do this just so I can show you. We can kind of remind ourselves of how to work with this. So indeterminate form of type 1 to the infinity. How do we solve that? Well, okay, well what we do here we first want to replace the n with an x and create a function, and that there's not going to be any issue there, and we're going to evaluate this limit, and then these two limits are going to be the same. So, all right, what do? We say that y is equal to that function, and then we take the natural log of both sides. So natural log of y is equal to x natural log of then we take the limit as x approaches infinity of this entire equation. So as x, let's create some room here. So as x approaches infinity, x over x plus 1, that goes to 1. And natural log of 1 is 0. 0 times infinity is another indeterminate form. So let's, the limit as x approaches infinity of natural log of y. Let's do this. We can, let's just focus on this limit here. So we've got x times natural log of x minus natural log of x plus 1. So we can do the limit as x approaches infinity of x times natural log of x. That's infinity. Then minus the limit as x approaches infinity of x times natural log of x plus 1. That also approaches infinity. So infinity minus infinity is an indeterminate form again. So we got a pain in the butt limit here. Indeterminate form infinity minus infinity. When it comes to the ratio and root test, remember we don't have to find the exact limit. If we can validate that the limit is going to be something that's definitely greater than or less than 1, then that's good enough for the ratio and root test. So, all right, so let's try this. We've got infinity times 0. This is indeterminate form infinity times 0. So what we can do is let's write it this way. So natural log of x over x plus 1 over 1 over x. So this approaches 0, this approaches 0 as x goes to infinity. So, all right, L'Hopital's rule. We've got 1 over, so the derivative of natural log of x over x plus 1 is 1 over x plus 1. So x plus 1 over x times the derivative of the inside. So, the derivative of the top is 1 times the bottom minus the derivative of the bottom times the top. So that's just 1 all over the bottom squared. So the x plus 1s cancel. So you have 1 over x times x plus 1. Now the derivative of the bottom. So you've got, all right, and then this x squared comes, so you've got minus x over x plus 1. As x goes to infinity, this goes to minus 1. But now that is, what we've got is the limit as x goes to infinity of natural log of y is equal to minus 1. So you raise both sides to e, and you get the limit as x approaches infinity of y is equal to e to the minus 1, 1 over e. That is less than 1, right? Because y is the original function. So that means that that means that this limit, the limit of this, is 1 over e. The nth root of a, the absolute value of a sub n, that limit is 1 over e. That's less than 1. So this is convergent. Well, by the root test, it's absolutely convergent, which means it's convergent. So I look at this and I'm thinking, let's just do the integral test. So x, if it applies. All right, is this decreasing, though, is the issue. So, okay, we think of the unit circle, right, as x is getting bigger and bigger and bigger, or you can think about n as getting bigger and bigger and bigger. You're approaching, the 1 over n is approaching 0 from the top, so we're coming here. What is sine doing? Sine is decreasing. So sine of 1 over n is decreasing, and then this is decreasing, so this is going to be decreasing. It's continuous decreasing, and it's positive as well. Sine of 1 over n is always positive. All right, so let's use our calculator. X times sine of 1 over x. Store that as e integral from 1 to infinity is infinity. So this is divergent according to the integral test. Again, don't get mad that I'm using a calculator. These problems aren't about integrals. We've done a large amount of integrals, and we could absolutely think about how to find this integral manually. I'm just not going to spend so much time in this video on how to evaluate integrals. All right, here I think about the ratio test. The ratio test is always nice with factorials. So, okay. Now, this is always positive, so we don't have to consider the absolute value. All right, so n plus 1 factorial, let's write that as n plus 1 times n factorial. And then we've got e to the n plus 1 squared. Okay, now we've got e to the n squared, and then n factorial. So, okay. Okay, so now let's write this as, so n plus 1 squared is what? N squared plus 2n plus 1. Okay. So we can write that as e to the n squared times e to the 2n plus 1. So we've got there we go. So what is the limit? Okay, let's write this as a function of x. Okay, there's no issue there. So now let's take the limit as x goes to infinity. Okay, as x goes to infinity, the numerator and denominator go to infinity, so L'Hopital's rule, and we've got, so 2e to the 2x plus 1, and this goes to 0, which is less than 1, so convergent. All right, so alternating series test. This is always positive. This is an alternating series, so let's first try the alternating series test. Okay, is this decreasing? Well, yeah, the order of the numerator is less than the order of the denominator. So that's not an official proof, but this is going to be decreasing. So, okay, so the limit as j approaches infinity of the b sub n we just talked about is going to be equal to 0. And so that, by the alternating series test, this is convergent. All right, an expression like this with, a ratio of polynomials or radicals, polynomials contained under radicals, we do a comparison test. That's we don't have to, but that's a good option. So we take the comparison we're going to do is we take the order of the numerator we see as n squared divided by the order of the denominator. So okay, how does the original a sub n compare to the b sub n? And so with n squared over n cubed, that's what this is. What we did was you can think about that's like, well, okay, yeah, we can do this. We can take out an n, and does that help? Yeah, because now we just need to look at what does square root of n squared, the difference between these two is the square root of n to the fourth plus 1 over n squared plus 1, right? So n is always greater than 1, so what does that mean? That's kind of confusing too. Well, okay, let's go back. Okay, so n to the n squared over n cubed, so we've got this square root of 1 here, okay, no, we took out this 1 and we took out this n. So yeah, I mean, maybe that should mean that, right, we're always adding an n in the denominator. So I'm thinking that would be, this is like that, right? We add a 1 up here, which makes this bigger. We add an n down here, which makes this smaller, but we're always only adding a 1 up here, but, you know, getting bigger and bigger and bigger. We're adding bigger and bigger numbers down here, right? Because we're thinking about it like the square root of n to the fourth over n cubed is this. So the only difference is the plus 1 up here and the plus n down here. And the plus n, so that's going to mean that this is always less than this. Okay, so this diverges, and so this test is inconclusive. Okay, so in that case, then let's just go to the integral test, and we can use our calculator. So and I'm confident that we could do this manually, no problem. So I'm okay with using the calculator. If I didn't have the skills, and I was very confident in my skills to do these derivatives and integrals manually, then I wouldn't use the calculator. Okay. There's no issue there. Converting the n, or swapping out the n with an x. All right. So the square root of x to the fourth plus 1 divided by x cubed plus x. Store that as e. Now let's take the derivative of that and store that as d. Okay, so where does the derivative equal 0? It never does. So let's take the derivative and plug in any value of x that's greater than 1. So, 2. That's negative. And so the derivative will never change signs. So it's always decreasing. So we have a continuous positive decreasing function here. So it's eligible for the integral test. So 1 to infinity what is this? Okay, so 1 to infinity of e is infinity. So this diverges. Okay, so is this an alternating series? Yes, it is. This is always positive, so let's do the alternating series test first. See if that works. Okay, is this needs to be decreasing. So let's just use our calculator to see if it's decreasing. So x squared minus 1 over x squared plus 1. Okay, the derivative, store that as d. Okay, at x is equal to 0, it's equal to 0, and it's positive everywhere else. But then we see that that derivative is not negative. It's actually positive. So if we bring in the graph of x squared minus 1 over x squared plus 1, yeah, so it is increasing. But it's like, it looks like it's increased. It has a horizontal asymptote at 1, but we can't do the alternating series test here. We can't do the integral test here either. Well, okay, let's, this does simplify to, we've got, this might be helpful. Or no, that's not going to do anything. Okay, nope. All right, let's do the ratio test. So we're doing the absolute value, so we can just take out that minus 1 to the n. All right, so n plus 1 squared minus 1 over n plus 1 squared plus 1 times n squared plus 1 over n squared minus 1. So we've got n squared plus 2n plus 1 minus 1. Okay, and then we've got n squared plus 2n plus 1 plus 1. Okay, n squared plus 1, n squared minus 1. So we've got n times n plus 2. Okay, does this factor to anything? Well, okay, it doesn't look like we're going to be able to cancel. So let's just go ahead and do these multiplications here. So n to the 4th plus n squared plus 2n cubed plus 2n. All right. Then we've got n to the 4th minus n squared plus 2n cubed plus 2n plus 2n squared, no, minus 2n plus 2n cubed minus 2n plus 2n squared minus 2. So we've got n to the 4th plus 2n cubed plus n squared plus 2n. Okay, then we've got n to the 4th minus n squared plus 2n squared, no, plus 2n cubed plus n squared minus 2n minus 2. Now the limit as n goes to infinity of this is going to be 1, which is inconclusive. And actually, I should have known that, right? Anytime with these types, these are the limits of these are always equal to 1. Okay, no, I know. Yeah, okay, yeah. So that was a waste of time. I should have. The textbook said that a limit of a rational expression as n goes to infinity is going to be equal to 1 when it comes to the ratio test. Okay, no, I think I see what we need to do. Yeah, we need to test for absolute convergence. Is what we need. I should have been doing. I messed this up. What is this series convergent? Okay, well, we do the comparison test, right? We're going to compare n squared minus 1 over n squared plus 1 with n squared over n squared, so with 1. This is always less than this. This is divergent. So that's inconclusive. Well, no. This is the test for divergence tells us that this is divergent. Yeah, okay. Let's do the okay. The test for freaking divergence is what I should have started with here. The test for divergence. What is the limit as n approaches infinity of minus 1 to the freaking n, all that work? What is this limit? This goes to 1. Minus 1 to the infinity is oscillating between 1 and negative 1. That's an oscillating discontinuity. This is divergent, so this is divergent. Damn it. Okay. Test for divergence. The idea is you can always start by looking at the a sub n of a series and seeing, okay, if I just take that limit as n goes to infinity, is that not going to be equal to 0? If that's the case, then it's divergent. All right. Okay, I'm thinking here the integral test. So okay, this is always decreasing. It's always positive and it's continuous, going from 2 to infinity. So what is the integral? So let's use our calculator here. That is convergent. This is convergent, so this is convergent. Okay, so I want to try the ratio test here. This is not a rational function or anything. And, you could think about we do a comparison test, but that seems kind of tricky in this case. So let's see what happens with the ratio test. This is always positive, so all right. N plus 1 squared plus 1 over, so 5 to the n times 5 to the first, and then n squared plus 1. Okay. So we've got, all right, expanding this out, we've got n squared plus 2n plus 1 plus 1, n squared plus 2n plus 2 over n squared plus 1 with a 5 out front. So what is the limit as n goes to infinity? We bring that 5 out of n squared plus 2n plus 2 over n squared plus 1. This limit is 1. So 5, that's greater than 1. So this is divergent. Or wait, no, I'm sorry. This is 1/5 out front. Not 5, right? This is in the denominator. So this was a 1/5. One-fifth is less than 1, so this is actually convergent. Okay, so here we can write this. I wonder if this reveals anything. So n 1 plus cosine squared. I feel like maybe we can do a comparison test with this. Yeah, let's try a comparison test. So how does 1 over n compare with okay, this is going to be always positive, and it's going to be, we can think about cosine squared of n would be between 0 and 1, but technically it'll probably never be equal to 1 or 0. So this will be between 1 and 2. So this is less, right? This is always some number that's greater than 1. So this will always be less. This diverges, so this is inconclusive. The comparison test is inconclusive. All right, now I'm thinking about the test for divergence, but we can see that this limit's going to go to 0, so that's not going to tell us anything. What about the integral test? So this is, yeah, let's try that. This is going to be decreasing. If we, this f of x, this is decreasing, continuous positive. So, okay, what is the integral from 1 to infinity? So x plus x times cosine x squared 1 over that. Integral from 1 to infinity. Okay, it looks like it's taking a little while to do it, so maybe it's not going to be able to get an answer here. So if it doesn't give us an answer, then what do we do next? Okay, it did give an answer, but what's the warning? Questionable accuracy. Okay, but it does converge, so convergent.